Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Yes, this is my channel. Please subscribe my channel if you have not already subscribed. Thank you. Right. We continue the discussion of the solutions of the problems that has appeared in the CSIR National Eligibility Test July 2025. In this video, we discuss the solution of a problem from the section linear algebra, and it is related to the commutator of two linear maps. This question is placed in part C, which is a multiple select question. There may be more than one answer and it carries 4.75 marks. The question ID is 562954149. This question is suitable for all these examinations. Right. The given question is, let S and T be C linear transformations from C square to C square, and I denote the identity transformation on C square. Which of the following statements are necessarily true? We are given four options. Option 1, St minus Ts whole square is equal to lambda times I for some lambda belongs to C. Option 2, the characteristic polynomial of St minus Ts whole square is x minus lambda whole square for some lambda belongs to C. Option 3, if St minus Ts has only one eigenvalue, then St minus Ts is lambda times I for some lambda belongs to C. Option 4, if St minus Ts has only one eigenvalue, then St minus Ts whole square is the zero transformation. Right. Let's now discuss the solution of the problem in detail. We have S and T are C linear transformations from C square to C square. We take S and T as the 2 by 2 complex matrices for convenience. Right. We call on option 1, St minus Ts whole square is equal to lambda I for some lambda belongs to C. Let A be St minus Ts. What is this St minus Ts? S and T are two C linear transformations from C square to C square. St minus Ts is called the commutator of the two linear maps S and T. Right. Let us take A is St minus Ts. Then trace of A is equal to the trace of St minus Ts. That's equal to the trace of St minus the trace of Ts. And this is equal to 0 because the trace of St is equal to the trace of Ts. We know this one. Agreed. For any 2 by 2 matrix A, the characteristic equation is given by x square minus the trace of A multiplied by x plus determinant of A is equal to 0. Agreed. But we have the trace of A is 0. So that will be x square plus determinant of A is equal to 0 because the trace of A is 0. That will give rise to x square is equal to minus determinant of A. This is the characteristic equation, what we got. Let's call this as the 1. We require this. Right. So by Cayley-Hamilton theorem, every square matrix satisfies its own characteristic equation. We have the characteristic equation is here, and A satisfies this one. Therefore, A square is equal to minus determinant of A multiplied by I. multiplied by I. So what is a square? What is a? St minus Ts. So thus St minus Ts whole square, in the place of a we have written St minus Ts whole square, is equal to lambda I, where lambda is minus determinant of A which belongs to C, because the elements of A are complex numbers. Agreed. Agreed. Thus the option 1 is true. We move to the option 2. The characteristic polynomial of St minus Ts whole square is x minus lambda whole square for some lambda belongs to C. From this equation 1, equation 1 is x square is equal to minus determinant of A, where x is the eigenvalues. So therefore the eigenvalues of A are given by under the plus or minus under the square root of minus determinant of A. So let lambda 1 is equal to under the square root of minus determinant of A, and lambda 2 is equal to minus under the square root of minus determinant of A. Right. And now the eigenvalues of A square, because we want A is St minus Ts, na? So we want St minus Ts whole square. So A has eigenvalues lambda 1, lambda 2. Therefore A square will have the eigenvalues lambda square, lambda 1 square and lambda 2 square. But you see lambda 1 square is equal to lambda 2 square is equal to minus determinant of A. So A square has only one eigenvalue, namely lambda 1 square, that is minus determinant of A, with algebraic multiplicity 2. Therefore, the characteristic polynomial of A square, that is St minus Ts whole square, is x minus lambda whole square, where lambda is equal to lambda 1 square is equal to minus determinant of A. Thus, option 2 is true. Right. We move to the next slide. Right. Let's remember, we said A is St minus Ts, that is the commutator of two linear maps. The characteristic equation of A is x square minus determinant of A, which we called it as 1. And by Cayley-Hamilton theorem, we have seen A square is equal to minus determinant of A multiplied by I. So thus St minus Ts whole square is lambda I, where lambda is minus determinant of A belongs to C. Call it as 2. Right. We require 1 and 2. So option 4. If St minus Ts has only one eigenvalue, then St minus Ts whole square is the zero transformation. From 1, the eigenvalues of A are lambda 1 under the square root of minus determinant of A, and lambda 2 under the square root of minus determinant of A. So A is equal to St minus Ts. A is equal to St minus Ts has only one eigenvalue. That means lambda 1 must be equal to lambda 2. That is under the square root of minus determinant of A is equal to minus under the square root of minus determinant of A. That will imply determinant of A is equal to 0. Right. Therefore, get into the equation 2. St minus Ts whole square is lambda I, where lambda is minus determinant of A, but determinant of A is equal to 0. Therefore, lambda I is equal to 0. Thus the option 4 is true. Right. Now we move on to the last third option. If St minus Ts has only one eigenvalue, then St minus Ts is a scalar matrix, that is lambda I for some lambda belongs to C. So we give a counter example. Let S is the 2 by 2 matrix 1, 0, 0, 0. T is the 2 by 2 matrix 0, 1, 0, 0. We compute St minus Ts. Yes, St we computed this one. Minus Ts is this one. Please do it and subtract. You will get 0, 1, 0, 0. Right. But what is this matrix? St minus Ts. And what are the eigenvalues? What are the eigenvalues? Determinant is 0 and the trace is 0. Therefore, the eigenvalues are 0, 0. So, 0 is the only eigenvalue of this, but this matrix St minus Ts is not a scalar matrix. Lambda is not lambda I for any lambda belongs to C. Therefore, option 3 is not true. It has only one eigenvalue, namely 0, but St minus Ts is 0, 1, 0, 0, which is not equal to lambda I for any lambda belongs to C. Therefore, option 3 is not true. Summarizing all the options, the answer to this question are options 1, 2, and 4. That is the detailed discussion of the solution of the problem from the section linear algebra, which is based on commutator of two linear maps. Yes, it is an interesting question. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Yes, this is my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure I will be meeting all of you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.